Welcome to qnawire.
Now, in this question, we are investigating the doublet that we observe in the HCl, hydrogen chloride molecule spectrum, right? The rotational spectrum. And the reason behind this is because there are two isotopes of chlorine that is quite common, that is chlorine 35 and chlorine 37. Because of their different masses, they have different rotational energies, and as such, the photon that is emitted or absorbed is slightly different, right? Only very slightly different, resulting in a small splitting in this spectrum. So we're going to see what is this, how much is this split, right? So we're going to start off by assuming a general reduced mass to find what is the wavelength, right? That is the one that we want. We want to find the wavelength or the longest wavelength. So starting off, we have energy of the rotational energy of any state is given as h bar square over 2I times j plus 1. Now, since we want to find the longest wavelength, we are simply looking at the smallest energy difference, right? And the smallest energy difference comes from between j equals to 0 and j equals to 1, right? That will be the smallest possible energy difference, which is h bar square over 2I. J equals to 1, this will be 1 times 2 minus j equals to 0, which is just 0. So this h bar square over I. From here we can find what is the wavelength, given that this is the energy of the photon. So this is hc over lambda. So lambda is just c times I divided by h bar. So, and then we have 4 pi square at the top, because h bar is just h over 2 pi, right? So if we convert this, this will be h over h square over 4 pi square, right? So then we get this expression. Now for the moment of inertia I, that I is equals to mu, the reduced mass, multiplied by the interatomic distance between the molecules squared. So this mu times r square. Putting it into here, get 4 pi square c mu r square divided by h. So we can actually evaluate this expression except for the mu. So we're gonna leave the mu outside over here, and the rest of this inside the brackets is actually constants, right? So we can actually substitute the values in for the constants, and we're gonna use quite a high significant number for all of these values, because what we're comparing later is a very small difference, right? So we will have to keep some extra significant digits, right? So for C, speed of light, can use for the R is given. Then for H, Right, so evaluating this, we get so this is the expression that we get in terms of mu. So we will need to find out what is mu, add it in, then we will get our wavelength in terms of meters. So for the first part, we are looking at chlorine 35. So for chlorine 35, we want to find the reduced mass. Take the mass of hydrogen, multiply by the mass of the chlorine, then we add them together. This will be in terms of atomic mass units, right? Since we have U square at the numerator, but only U at the denominator. So we gotta convert this into kilograms. So this is the conversion factor. So using this reduced mass, we put it into the previously found equation, which is this equation over here. Substitute that in to get the wavelength. And then we should get about 4.72 times 10 power minus 4 meters. And this is also equals to 472 micrometers. And now using the same method, we can find the reduced mass for our chlorine, our molecule containing chlorine 37. It is the same process, except that now the mass for chlorine is 36.965903. Right, so for this, the reduced mass is 1.629118. And with this, we can find the wavelength to be 473 micrometers. So very, very close to our previous answer. So in order to find the separation, we have to use a higher significant digit. So over here, the answer previously is about 472.0270 micrometers, whereas over here this is actually 472.7424. micrometers, right, in higher digits. So the difference in the wavelength is probably around 0.715 micrometers.